All right, so good evening and welcome back. Yeah, this week is a little bit special because tomorrow is Golden Week and few students cannot come today. They will watch the record. Before I forget, last week I forgot to ask you to sign for attendance. I'm not very strict, and in fact, I'm not even going to use this at the end of the semester, but it's just an idea. It gives me an idea. So please, if you were here last week, sign for last week as well. You will get the sheet very soon. If you are not here, just sign for today. Okay, let me just remind you what we have done last week very quickly. You remember distributions are defined on a small set of functions, the test functions. We would like to extend this to a broader set of functions. And there is this notion of summable distribution. I don't recall the definition, but last week I explained what means summable distribution. And I introduced also what is a summability order. And whenever you can check that the distribution is indeed summable and has a summability order M, you can extend it, so you can apply it to a much larger set of functions, which is a set of continuous functions which are M times differentiable, and all derivatives are bounded. So if you think about this, this is much bigger because it doesn't even require the function to be of bounded support. The function 1 is in this set, for example, while it is not in the set of test functions. So we can extend summable distributions, and we even have a certain formula how to define a distribution which is M summable on a F which is on this set. You take a function, a test function which is 0, which is 1 at 0. You take a F in this bigger set. You define this approximation of F by this product of G of X over Y times F of X. And you have this. So this function is much better than F because it has a bounded support if you can check it easily. So this is for the extension. And then I define this Fourier transform. The Fourier transform is very useful in many fields on many times. It's a useful transformation. I gave a formula and I define it, be careful, for function in L1. L1, I just remind you, F is in L1 of Rn if you can take an integral. So it means if the integral of f of x in absolute value or modulus dx is finite. So it's a strong condition which says that the function is integrable. But the Fourier transform is well defined on this, and some properties of the Fourier transform can be checked. It doesn't matter if on the website there is already 1 or 2 reports on this. You can still work on this as long as you understand what you are doing. And I mentioned a very important result for quantum mechanics is that F can be extended to a bijective and isometric map on this space. This space, I also recall, F is in L2 of Rn. If you can take the integral of f of x square dx, and if this is finite. Be careful, these two conditions are not the same. Once you take a square, the other one's not. And this is useful in quantum mechanics. And what means isometric? It means the norm of f in this space. And what is the norm in this space? It's precisely this integral, and then you take the square root of the number. This guy is equal to the norm of f in L2 of n. So it means the Fourier transform has a very nice property in this space. And we would like to study how a Fourier transform acts on distribution, but we face a first problem, is the Fourier transform of a test function is never a test function. So it means this set of test function is too small because when you apply f, you are no more in this set. So we are going to find a larger set. This larger set is made of Schwarz function. I do not recall the definition, but the set of Schwarz function is denoted like this. And essentially, Any Schwarz function, you can take any derivative, multiply by any polynomial, take the sup norm, so you take the absolute value, and then the supremum, it's finite. So it means f has to decay faster than any polynomial. If you think about this, you multiply by a polynomial, f or a derivative of f, it's still bounded. And it's still bounded. So f is decaying faster than any polynomial. And we have these inclusions. The set of test function is included inside the set of Schwarz function. It's not equal. And I told you can easily find an example of a function which is here but not here. Then this set is inside the set of smooth function with all derivatives bounded. It is inside the set of all functions which are smooth without any condition about the decay. Is it inside L1 lock? I told you N1 lock is very big. It is this condition, but which has to be true only on a ball of any radius on any center. This is a very big set. And this, we have this inclusion. Be careful, this inclusion is maybe not so straightforward. Take a H here. It is inside the set of distribution by identifying H with its regular distribution. I introduced this. And the very good point with this set of Schwarz function is this equality. It said that if, and it's not completely straightforward. I mean, you have to work a little bit for this, but I give you this result. Any function in the Schwarz space, take its Fourier transform, it is again in the Schwarz space. And it's even an equality, it's not only an inclusion, it means any function in the Schwarz space is the Fourier transform of somebody. So it means this map is bijective. You can go in both directions. So this is very important. And I finally mention one additional property of Schwarz functions and Fourier transform. Take a Schwarz function, take any derivative. I told you for some reason we have to put a minus I. This is not the main point. But it says that take any derivative, take any polynomial, apply the Fourier transform, then it is equal to, the Fourier transform a polynomial into some derivative, transform some derivative into multiplication by a polynomial. So this is also an interesting exercise. You can start with just one derivative, one polynomial, and then you extend it. Do you have any question about what we have done last week? So again, you can ask me also a question by email or any way. Or you can ask your tutee or your tutor to answer the questions. So today we are going to finish this subject with Fourier transform. So this is our starting point. Remember when we defined distribution, so let me just remind you one more thing. When I define d prime of Rn, it was a set of functions from the set of test functions to k, so that t of fj converge to t of f infinity. This was one condition. For any sequence fj of test function converging to f infinity. So now I need to replace this. I need to replace this condition because I'm going to deal with a new set of functions. So what means fj converge to f infinity? Is there any question? So I need to define, this is the first definition, the notion of convergence. Convergence in the Schwarz space. And remember, the Schwarz space is bigger than the set of test functions. So let me write the definition. A sequence fj, any integer, inside the set of Schwarz space converge. When you see the definition, it converges to F infinity in this Schwarz space as J goes to infinity. And now I need to say the meaning. If it's the one. If limit when J goes to infinity of, let me write it and then I explain beta x. So what does it mean? First, let me remind you what means this infinity. It means the supremum over all x in Rn of x beta d alpha f at x fj minus x beta d alpha f infinity at x. So this norm with an infinity mean takes a supremum. So it says that fj is approaching f infinity, but this is the same for all derivative. And in addition, you can multiply by a polynomial, and it's still going to 0. You have a question?
Sorry, why is the derivative outside of the x? You think the derivative?
Oh, sorry, I exchanged the order. It doesn't really matter, but you're right. I can put in both order. I need to be coherent. Yeah, that was a question. Yeah, sorry. In fact, you can exchange because you would get terms of lower order, but this is not important. So it means really all derivative, the difference of these two functions decay faster than any polynomial, since you can multiply by any polynomial. So think about it. And in this case, so if this is true in this case, we write that limit j goes to infinity of fj is equal f infinity in this Schwarz space. So if you remember what I defined for convergence in the set of test function, it was essentially the same, but without this x beta. Why? Now it's slightly different. For a test function, these functions are with bounded support. So polynomial doesn't change so much on an interval. If you think about an interval, a polynomial is always finite on an interval. Now these functions are not with a bounded support. They can go up to infinity. So this is really a condition. Multiplying by a polynomial, it said that the function has really to decay faster than a polynomial. So it's slightly more complicated than for test functions because you have this additional polynomial. But now we have this notion of convergence in the set of Schwarz function. So I can define what is a distribution for the Schwarz space. So definition. The distribution T inside the set of distribution is a tempered, so this is a definition, it's called a tempered distribution. If T of Fj goes to T of F infinity whenever Fj converge to F infinity in S of Rn. I will make a picture in a second. So this is a definition of a tempered distribution. And we will see that it's slightly different than the regular distribution, than arbitrary distribution. Let me make a picture first. As I said before, the set of test function is inside the set of Schwarz function. In fact, it's even small, but we have the set of test function, we have the set of Schwarz function. Now remember, a distribution is a map from D of Rn to K. This is a distribution. A usual distribution in the sense I introduced already 2 weeks ago. And now a tempered distribution it goes from the set of Schwarz function to K. So which one is give you more constraints? Is it to go from this space to K or to that space to K? So in other words, if I do now the same picture for distributions, if I draw the set, two sets, which one is, can you tell me which one is S prime? I didn't introduce the notation. And which one is D prime of Rn? The set of tempered distribution, I should have mentioned it before. The set of tempered distributions is denoted by S prime. S prime. So can you tell me the smallest one? Is it S prime or is it D prime? Yes, S prime is here and D prime is here. Think about it. This condition is stronger than the one I introduced 2 or 3 weeks ago. Can you give me an example of somebody here? Can you give me a distribution which is in D prime and not in S prime? Be more precise. Consider h of x. Let's take e power x squared. This function grows very, very fast. And construct the th. So remember the regular distribution, th on a f is the integral on Rn, h of x, f of x, dx. And if h is this function, it makes, I can do it in n. Okay, we can do it in 1 dimension, it's simpler. Yes, but I can do it in 1 dimension, it's simpler. So we have the integral of e x squared f of x dx. So think about this integral. If f is a function is a test function, so if it has bounded support, you can always define this, no problem. Now, if f decay faster than a polynomial, So it goes like 1 over, at infinity, it goes like 1 over x 26, faster than any polynomial. Can you define this integral? No, because this is going exponentially. This one is decaying like a polynomial, so this number would be infinity. So this th with this specific h is here. You can apply it, so you can apply this th to a test function because f would have bounded support. So this integral is in fact an integral on an interval. If you try to apply it to a Schwarz function, in general, it wouldn't be finite. So it means there is a difference between this set of Schwarz tempered distribution and this set of distribution. All right? So it's good to keep this in mind. Do you have any question? You can always interrupt me at any time. So it means I haven't finished the construction yet, but this space is slightly bigger than this one. So it means the set of distribution, so the set of functions from this space to K, which are continuous, is slightly smaller. Now, let me just state one result, which is not so important, but I stated something similar for regular distribution, so I have to do it also in this framework. Let's say it's a lemma. T is, it's a tempered distribution if there exists a C bigger than 0, there exists a M integer such that T on a F is smaller, absolute value, smaller or equal to C times some alpha, multi-index alpha smaller or equal to M T, no, D alpha F infinity. No, sorry, I'm doing a mistake. Yes, X beta D alpha F infinity for any alpha beta multi-index, both smaller or equal to M. So if you come back to a similar result for regular distribution, it was a regular distribution, not regular, a distribution, that's it. A distribution has to satisfy that there exists a C, there exists a M, such that this is true for all F in the set of test function. And as I already mentioned, for test function, you don't need this polynomial. So here it's something similar. T is a tempered distribution. If there exists a C, there exists an M, such that you have this inequality for all F in the set of Schwarz function. So I wanted to say this because I presented something similar before. And now we get the main result of this section. Remember, I introduced this set for Fourier. I introduced my purpose or my aim was to discuss Fourier. And I already know that the Fourier of Schwarz function is a Schwarz function. So now I'm going to use this information. So this is the main definition of this section. For any T tempered distribution, so S prime of Rn, we set Fourier transform of T. This is what I wanted to define. I wanted to define the Fourier transform of a distribution. And I already wrote this formula last time. Evaluate on F, by definition, it is T of F. And now you can see why this is well defined. And I should write for any F in the set of Schwarz space. Please think about this for a second. Why is it well defined? If I take a F in this set, the Fourier transform is in this set. So it means this guy is again in the set of Schwarz function. And precisely, a tempered distribution, you can apply it to a function in the Schwarz space. So this is well defined. And so I define the Fourier transform of T evaluated at F is this guy. The right-hand side is well defined. And so it means this one is again a tempered distribution because you can apply it to any Schwarz function. And in fact, I can even say a little bit more. So this is, in fact, if we consider F as a map from S prime of Rn to S prime of Rn, and look, this is exactly what we are doing here. I'm taking a T in the set of tempered distribution, and I'm getting a new tempered distribution. This map is bijective. And in fact, since F from the set of Schwarz function to the set of Schwarz function is bijective. So this is a very nice feature of this theory because the Fourier transform is bijective. So remember, bijective means you have two sets. It's a one-to-one correspondence. So because you have this one-to-one correspondence for the set of Schwarz function, you get it as a one-to-one correspondence on the set of tempered distribution. Any question or remark? So now for tempered distribution, we have a notion of Fourier transform. So it means, oh, I should have kept this picture. It was like this. We had D prime of Rn. We have S prime of Rn. This was the picture. It means now I have defined a map from here to here, which is Fourier. The Fourier takes any tempered distribution and send it to a new distribution. On the other hand, Fourier is not, you cannot define it here. There is no way, there is no Fourier transform. No Fourier transform. We cannot define a Fourier transform on this set. because you don't have such a formula. If you take a f, which is a test function, you're no more in the set of test function. So the yellow row is okay. The red one simply does not exist because you cannot give a meaning to this. Okay, now I have a few exercises on. It's certainly good. They are not complicated. These ones are very easy once you look at the definition. So exercise. Even first-year student, I encourage you to look at this exercise. Prove the following equalities. What is the Fourier transform of delta zero? First, in fact, we should check that delta zero is here. So the Dirac delta distribution at zero, we should check that it is indeed a tempered distribution, but this is not difficult. So I can apply Fourier transform because it is in this set. And I'm claiming, or you have to show that it is a tempered distribution for special h. H of x is a constant. It's 1 over 2 pi n over 2. This is constant function. And this is something you are going to use for the breakfast, for lunch, and for dinner every day. If you are in physics, if you are in engineering, you are going to use this many times. The Fourier transform of the Dirac delta distribution is a constant function. It's an equality between two distributions, two tempered distributions. So please remember this, and it's easy to check once you have this framework. What is the Fourier transform of T1? What means T1? It's a constant function, which is 1. So you have to check first that T1 is again here. It's a tempered distribution. And the Fourier transform of this tempered distribution, it is 2 pi n over 2 delta 0. In fact, these two exercises are exactly the same. If you think about it, they are very, very similar. Because Fourier transform is bijective in this set. Another one which is interesting, Fourier transform of TH is TH Fourier, but this is not for an arbitrary H. So it means I have to say who is H for any H in L2. Remember when I recalled at the very beginning, I told you F has an extension from L2 of Rn to L2 of Rn. I mentioned this. So here the claim is take the Fourier transform of the regular distribution of a function h in this space. And by the way, I recall that L2 is inside the L1 lock. So you remember TH was defined for L1 lock. I told you for a very, very big set of functions. So if H is in L2 and L2 is in L1 lock, this is well defined. So the claim is for H in L2, TH is again a tempered distribution. And its Fourier transform is a distribution, it's a regular distribution given by the function h hat. This is not difficult if you write just the expressions. This is essentially what you wanted to have before. Now it's well defined. And the last one I ask you to do, because I don't know the answer, so please try to find the answer. What is the Fourier transform of t of the function h with h of x, but in one dimension, it's is x squared? And this is again is useful in physics or in engineering. So take the function x goes to x squared. It's in L1 log. But first check that this, here you have this t, x goes to x squared. Sorry, it's a little bit small, but I just want to say, check that this regular distribution is in fact a tempered distribution. So you can take the Fourier transform, and the Fourier transform is something. And please compute this something. But this story is really, really important for these two lines. And for the, these, in fact, for all of them. These 4 examples are really, really important. But in order to compute them, you need the notion of tempered distribution and the notion of Schwartz function. So I encourage you to work on these 4 examples, because this is really the way you are going to understand what is going on. Any question or remark? Good evening. If you have any question, you can always ask me. So with this, I finish already the chapter on distribution. Of course, it's a much longer subject, but if you already remember what we have seen, you can face your course of most of the courses on this in this university. This is all what you need. But of course, you can go much deeper. But what you're going to use, I have introduced it. Okay, so take a 1-minute break, and then we move to a new subject. So if you haven't done any exercise yet, I encourage you to look at these ones, or this one. It's good to work on this. And try to keep in mind these pictures. We had, before I have written the set of test function on the set of Schwartz function, which is bigger, but it means for distribution, the set of distribution is bigger than the set of tempered distributions. But nevertheless, these 4 examples are inside this set. And I already mentioned one example of which is here. It is a regular distribution with this exponential of x squared. Is it a really established result that if you have 2? Please, I cannot hear the question. Yeah. Is it really an established result if you have, let's say, 2 spaces, one's bigger than one equals the other? Then a function from the bigger space, the set of all functions from the bigger space will always be smaller than the set of all functions from the smaller space. Yes, he's asking the picture I did before, and the answer is yes. If, at least in general, like in general, if you have 2 sets like this, and then you look at function from this space to K, or from that space to K, then satisfying a certain condition, then If you have to check it on a bigger set of functions, it's more difficult. So it's going to be, you have more constraints when you check it on a bigger set. So you have less. So yeah.
And then automatically, then the functions from the bigger set always satisfy the smaller set condition.
Yes, because if a function satisfies a certain property from the bigger set to K, it also satisfies from the small set because it is inside.
I see, but this will only work if this method is completely included in the bigger set.
Yes, indeed. If you have something of this type,
Then no.
if you have something of this type, you cannot conclude because this set is not comparable with this one. So I couldn't say anything if we were in this situation. If we had the set of test function here, of course, this is not true. On the set of route function, if we were in this situation, the story would be completely different.
And we can't say anything about this.
And we cannot say so much in this situation, but fortunately, this is not true. We have something really like this.
Thank you.
Yeah, whenever you ask a question, don't be surprised that I need to repeat the question because the one outside cannot hear the question. That's normal, yes, but this is something we have to think about. Chapter 2, Lebesgue theory of integration. So essentially, we would aim to give a general meaning to integral of f of x dx. Would like to give a meaning to this. This is something you already look at in high school. This is something you look again at in Calculus 1. This is again something you study in Calculus 2 in n variables, but still we are going to do something more general. Okay, and I will start by recalling what we have studied in Calculus 1. So if you haven't done Calculus 1 now, the first year student, first semester, I'm going to already teach you something that you're going to learn in probably 1 or 2 months, very quickly. For f, of course, it's a function. I should do it in this general framework, but I will not do it in this general framework because it would be slightly too complicated. I would just stick to the case n is equal to 1 dimension, and for simplicity, I will do it for R, but at the end, I will just explain how to extend this. So it's not a big restriction, and it simplifies some expression. So I'm going to define this integral for f of one variable with value in R. So as I said, I will start by recalling what you learned in Calculus 1. So section 2.1 is a reminder on Riemann integral, on Riemann integration. And if you haven't studied this before, then it's not a reminder. It's a very short course on Riemann integrals. So I will consider an interval, or I consider an interval in R with A strictly smaller than B. So it means I'm really on the line and I consider AB like this. I don't want to have interval which is just 1 point. I'm going to subdivide it. So I'm going to divide this interval into smaller parts. This is called a partition. So I define an n partition. N partition. N is just any integer. N is any integer. N partition, and I give a name, P of AB is P equal to x0, x1, x2. It's n points, sorry, n plus 1 points. Check if I start at 0, we have 1, 2, 3 up to n, but it makes n plus 1 points. And I impose that x0 is A, and I impose that xn is B. So on this picture, I'm simply, oh, let me do it bigger. A partition is this. We have A, we have B, and I call A also x0. I'm choosing x1, x2, x3, x4, x5, and let's say x6. This is an example of a 6 partition. A partition is just a subdivision of this interval into n subintervals. And I should mention xj is strictly smaller than xj plus 1, which means I don't take 2 times the same value. Right? I divide an interval. And now I consider a function on this interval. So I'm going to consider function f. This is f. So let's consider a bounded, and I need to explain what is a bounded function f from this interval to R. What means bounded? It means there is an upper value and there is a lower value. So it means, I just explain this bounded. F is bounded on AB if there exists m bigger than, or it can be 0, such that f of x in absolute value is smaller or equal to m for any x in AB. Look at my picture. Where is m? I can take m here. I can take this value because m is bigger than any positive value of f, and we would have minus m about here. And minus m is smaller than any negative value of f. So bounded function is a function which takes value between m and minus m. All right? So let me define the set of all bounded function, because I need this notation. The set of all bounded functions on AB is denoted by curly I do it a curly L on purpose. Maybe you cannot understand right now, but let me just stress one thing. You remember before I have introduced L1 of Rn, and I have also introduced L2 of Rn, and also L1 log. It's not the same L. You can see I'm using a different font. It's on purpose. I will explain in a few weeks why here I use this L, and this is a curly L. There is a small difference. So just use, please, this curly L. If you use the same L there will be a small problem later. So what is this curly L infinity? Let me remind. L infinity of AB is the set of F from AB to R such that sup of X in AB of F of X is finite. You can check it's the same. Because if it is finite, it means there exists M which is bigger than all possible values of F. So this is a set of bounded functions. For example, the function 1 over x, let me just give you this idea. The function 1 over x is not bounded at 0 because 1 over x goes to plus or minus infinity. So I should make a function which is not always continuous. Let me just draw a second one. I can also do a function like this. This one is not continuous. I'm not asking continuity, but still this one is bounded. On the blackboard, most of my functions are continuous, but this is a mistake. In fact, most of the functions are not continuous. So now we have two ingredients. We have an interval with a partition. I divided this interval into n pieces. By the way, these n pieces, I'm not asking that they are of the same length. Some can be longer, some can be shorter. That's okay. I don't impose any regularity. And we have a f which is bounded. So I'm going to set L of fp. I'm going to define also u of fp. So observe I'm using these two ingredients, f, a function, and a partition. Let me give you the definition. The sum j, 1 up to n of, I will do the picture. And something similar here, but with a supremum instead of an infimum. Okay, so let me again, I do this picture. What L and U stand for, it's for upper, sorry, this is lower, this L is for lower. It's called lower Riemann sum. It's a lower Riemann sum, and this U is for upper Riemann sum. So let me represent what I'm doing. I have this interval AB. And again, let me take a continuous function because it's simpler. And I subdivide it into some interval. Okay, so this is x0, x1, x2, x3, x4, and here we have x5. So it's a 5 partition. Look, what I'm doing, I take the first interval, I look at the infimum, so the minimum value in this interval, the function in this interval, and I multiply by the size of this interval. So the first guy is this one. Look, I take one value, the minimum value in the interval for j is equal to 1. It makes 0 between x0 and x1, then times the length of this interval. So I'm considering this area. For simplicity, please allow me to take only positive functions. It's a little bit simpler for my picture.
Oh, it looks worse.
No, no, no. Be optimistic. Okay, it's simpler to think about positive value. Then what is the second? In the second interval, I take the minimum value of the function on this interval. I multiply by the size of the interval. Then again, the minimum value, and I multiply by the size of the interval. Then this quantity, and then this quantity. So this is this guy, L, lower Riemann sum. I'm taking this product size of the interval times the minimum value of the function in this interval. And then you do the same with the upper value. Upper value, you take the maximum value in the interval and you multiply by the size of the interval. Take the maximum value in this interval, multiply by the length of this interval. Sorry, it's becoming nasty, but I'm sure you can do much better. Who doesn't understand my picture? You don't understand the picture? You understand, good. Who doesn't understand the picture? Vic, you understand, I know. So this is, and clearly you have an inequality. Clearly, the upper Riemann sum is bigger than the lower Riemann sum. Clearly, the upper Riemann sum is bigger than, let me write it in the other order. The lower Riemann sum is smaller than U of Fp. Okay. And you can even say a little bit more. So this is clear because in each interval, you take either the maximum value or the minimum value. And by the way, if you have a negative value, let's suppose the function goes to negative, then one contribution is going to be negative. That's it, no problem. If your function is negative, when you take the minimum value, you have a negative number, no problem. But observe that this is smaller or equal to b minus a times, sorry, I write it here, b minus a times the supremum of f of x on this interval, x inside AB. On my picture, the maximum value is here, so everything is smaller than this big rectangle, right? This is well defined because f is bounded. On the other hand, here it is smaller, or we have somebody which is b minus a times the infimum of f of x for all x inside AB. And in my initial picture, the minimum value of the function is here. So this left-hand side would be this rectangle here. And indeed, we have the white one, which is bigger than the red one, which is bigger than the green one, which is bigger than the blue one, right? This is quite clear. And this is well defined because F is bounded. Otherwise, you cannot do it. Any question? Simple. Now what happens if you subdivide? This is for a given P. Now I will do a picture again. I'm going to subdivide each interval. So I will take only 2 or 3 intervals because otherwise it's becoming nasty. Suppose I have AB. Let's take the simplest situation. This is x0. I just take one subdivision, x2. And let's see, we have the function like this. So if I do the same picture, minimum value. Yes, it is. Yeah. Told you, be optimistic. The minimum value is here. The maximum value is here. Now suppose I subdivide. I'm subdividing. I do one more subdivision. But let's look. Before we had the infimum over this full interval and the maximum value over this full interval. Now when I consider one more subdivision, what is the infimum over the new subinterval? Look, on this one, we have this. Maybe I do it with wavelets. And here, this is the minimum value on this interval. So when I do a subdivision, the minimum value is different. And the same for the maximum value. On the right, we have still this value. On the left, this is the maximum value on the left. And this is the maximum value on the right. So when you subdivide, observe that the maximum and the minimum can be different. So now let's try to write it this. So now I consider P prime a thinner partition. A thinner partition of AB. And so I have to say what it means. And it's quite simple. P prime is included in P. Remember, these are collection of points. I'm just saying P prime contains more points. But it also contains a point of P. It simply contains additional points in between. P prime contains the points of P plus other points. Now you can guess, or let's look at what we have. I'm claiming this. Look at this. I'm saying with P prime, the lower Riemann sum is bigger. Look, it's visible here. With P prime, it is this wavelet. The minimum is bigger than the other one. So when you compute the lower Riemann sum, this contribution will be bigger than the original contribution. So it takes 1 minute to observe this. On the other hand, for the upper Riemann sum, we have a decay, because the biggest value on a subinterval is always smaller or equal to the biggest value on a bigger interval. So please think about this. We are always in this situation. When you take a thinner partition, you have the inequalities in this order. If you're not confident, please make a picture and you will see that this is true. Yeah? Yeah, I define P as a set of points. It contains the one of P plus other one. As a set, look, P is, let's say, x0, x1, x2. And I do a picture. We have
You wrote that P prime is included in P when P is smaller than P.
No, but it's correct. Look, this is P, the point of P, and now P prime. Yeah, this is P prime.
Yeah, there's more.
Yes.
So all the points of P are included in
did I write it? You're right. I hope in my notes it's correct. On the lecture note. Sorry. P contains more, thank you. P contains, so this is P. P is here, and this is P prime. Sorry. Yeah. We are like this. P prime contains more point than P. So then I did what is written. P prime contains more point than P. Yeah, contains a point of P plus other. Then this is correct. This is correct. Here it was not correct. So this is the picture. P prime contains a point of P plus additional one. And then we end up with this. And now there is one definition, which is the main definition. You can wonder what happens if you take more and more points. And think about the picture. When you have a function and you subdivide into many subintervals, look, on each small interval, the maximum value and the minimum value are becoming very close to each other. So definition, F is bounded, is Riemann integrable, this is the definition, is Riemann integrable if on AB, is Riemann integrable on AB if the on all partition of L of Ft is the infimum on all P of mu of Ft. Please think about this definition. I'm saying that it's Riemann integrable if these two quantities are equal. When you take all possible partitions. So it's Riemann integrable if you take, so it means you take the supremum, the maximum value on all possible partitions. So do all subdivisions, and you get the same as when you take the infimum value of the upper Riemann sum on all subdivisions. So you can wonder, oh, it looks like all functions are Riemann integrable, at least on my pictures. But this is not true. And there is a famous counterexample. So be careful. Not all functions are Riemann integrable. So let me give you a counterexample. Counterexample. The counterexample considers a function f simply on 0, 1 with value in R. F of x, I give this example in calculus 1. It is 1 if x is in Q, a rational number is 0 if x is in R minus Q. If you have never seen this function, try to plot this function. Look at the shape of this function. Take the interval 0, 1. Take this interval 0, 1. Put the value 1 at every rational x. So whenever you have a rational number, put the value 1. Whenever you have an irrational number, put the value 0. But you have many, many irrational numbers, and you have many, many rational numbers. So what you're going to get is a picture like this. You would see two lines. You cannot see really the difference between these two lines. But this is 1 on all rational number. This is 0 on all irrational number. And now check, I don't do it, but check this function is not Riemann integrable. This is also an exercise that everybody can do. This function is not Riemann integrable. Please try to check, take the definition of Riemann integrable, compute this guy, compute this guy. You are going to see that this is always 1, this is always 0, so they cannot be equal. So it's a nice counterexample. So not all functions are Riemann integrable. However, let me go a little bit. I have written a little bit more in the text, but I don't really need it. There is a result. So let me state two propositions. If f is a continuous function, this notation means if f is continuous. F continuous on AB. Then f is Riemann integrable. It's not completely trivial. On a picture, it's trivial. Marin, you are no more with us. Please. On the picture, on what I did on the blackboard, it was quite clear that any continuous function, if you take a continuous function, you take these subintervals, many subintervals. On each of them, the maximum value and the minimum value are almost the same. And you can guess, not prove, but guess that a continuous function is Riemann integrable. If you want to do it precisely, you have to work a little bit. So, but this is a standard result. All continuous functions are Riemann integrable. And if you are a third-year student, maybe you have done this exercise in your final exam of Calculus 1. If f is increasing or decreasing, then f is Riemann integrable. So this is another result which can be proved. If you have a function which is like this, AB. If you have a function which is increasing, Vic, I think you had this at your exam, Calculus 1,
Yes.
An increasing function is always integrable. It has not to be continuous, or a decreasing function. If you have a function like this, it's also integrable. It's not straightforward, but it can be done.
Monotone something.
Yes, it's monotone increasing or monotone decreasing.
I can't remember the name of like the
Monotone, yes. So this is something you should remember with my definition, or with the definition of Riemann integrability. All continuous functions are Riemann integrable. All increasing function or decreasing function are Riemann integrable. Let me give you a third example, just for fun. And you can try to prove it. It's easy. If f of x is equal to 0 if x does not belong to an interval, I will explain 1 if x belongs to an interval with I included in an interval, then f is Riemann integrable. And this is not covered by the case 1 or 2 because the function f looks like this. You take an interval I, and you take the function which is 0, 1, 0. You take this function, probably I need to put, sorry, it is not in I. So this function is neither continuous, and it's neither increasing or decreasing, so it's not covered by these two first situations. Nevertheless, this function you can check if you look at the definition of Riemann sum. Why is it Riemann integrable? Take any subdivision. On any subdivision, there are two nasty intervals, but only two. This interval is nasty, and probably this one is nasty. Why? Because look, on this interval, the minimum value and the maximum value is the same, it's 0. On this interval here, the minimal and the maximum value of the function is the same. It's 1. Again, it's the same. Only on these two intervals, it is different. But when you take smaller partitions, so when you take subdivisions, more and more subdivisions, then the nasty intervals are becoming smaller and smaller. You still have one interval and one interval here, where the function takes somewhere the value 0 and somewhere the value 1, but it's becoming smaller and smaller. So when you write the condition for Riemann integrability, you will see that the upper limit or the lower limit converge to the same value. And the integral is, of course, just this area at the end. And something quite similar can be used for this one and this one. So we have a couple of results saying continuous functions are Riemann integrable, increasing or decreasing functions are Riemann integrable, this one. But by the way, you observe that the counterexample I gave before, which is like this, with 0 and 1, it's not continuous, it's not increasing or decreasing, and it's not a characteristic function. By the way, this is called a characteristic function. Sorry?
What 0 and 1?
The one taking value 0 and 1. My problem is I never know how to write characteristic. See, there is a H. Yeah. My problem is H. Characteristic function. Characteristic function means precisely a function taking 0 except on an interval where it takes a value 1. Characteristic function. All right. So this is essentially all you need to remember about Riemann integral. Partition, upper Riemann sum, lower Riemann sum, if these two notions coincide. And I should have written one more thing. Remark. I haven't introduced a notation. Remark. If f belonging to an infinity of AB, bounded function, is Riemann integrable, meaning, I recall the meaning, it means that the sup of overall partition of of L lower FP is equal to the inf over all partition of U of FP. I mean, this is an equality between two numbers. The left-hand side and the right-hand side are numbers. We write integral AB f of x dx for this quantity. But again, this is just a next notation for number. So the integral from a to b of f of x dx is a number that you obtain in this case. Okay, I will not start the new section right now. Let me just give you a flavor of what we are going to do next week. This is a reminder about Riemann integral. Now, just in the next section, I would like to say this is a subset of Rn. What is the volume of this? How do you define the volume of this set? How do you, if you need to cover this with paint, how do you compute the volume of this? We are going to do it like this, indeed. I'm going to cover it by boxes. I take a cover, I will explain this. I take a covering by boxes like this. They have to overlap. Okay. I'm going to take a covering by boxes like this. Then for boxes, it's easy to know the volume. And I'm going to take the minimum value of such covering, which means I'm going to do a covering which is at the end is made of very small boxes. Nevertheless, it's not enough. It means if this is a cauliflower, you are not going to get a good notion of volume. Try to measure the volume of a cauliflower. It's not easy.
Not fun either.
Yes, it's fun. And it's good. The taste of a cauliflower is good. Okay, so we are going to give a meaning to what is a volume. And then once we have the notion of what is a volume, we are going to extend this notion of Riemann integral. So this is what we are going to do next. Do you have any question or remark? So I know the clock is not correct. So what's the exact time?
7:58.
Okay, 58. I give you 2 minutes. But do you have any question?
If you want to measure the volume of cauliflower, put it in water and do it like Archimedes did.
Okay, but if you put it in water, are you sure that what you really measure is really the volume of your cauliflower?
No, there's supposed to be air inside.
There is an error. And if you eat part of it, then it's even more nasty. Okay, so we are going to do this next time, define the volume of an arbitrary set and see that we have some sets which are complicated and we need to eliminate them. So we are going to say what is a Lebesgue measurable set. And by the way, on the website, you can find a new reference book, which I'm going to use for this subject. It's called Lebesgue integral or integration of Lebesgue. Okay. Any question or remark here?